yours. Well, it's not good morning, it's good afternoon. That's what I normally say. It's great to have everyone here for another Mesh Energy webinar. As you can see, today we've got Jasper with us. He's going to be going over waste as material, energy efficiency, timber framing, and air tightness. It's going to be a really great webinar, so make sure you get your questions in. Before we get started, I just want to go over some housekeeping. Can you make sure you keep your microphones on mute throughout the presentation? If you've got any questions, pop them in the chat box. This webinar is being recorded and will be put on Meshwork afterwards. As you all know, we're working really hard to develop Meshwork into a collaborative environment. We've got some exciting speakers coming up over the next few months. Next month we're covering COP26, which will be really good. So make sure you check out our events. They'll be posted in the next few days, hopefully. And yeah, it's completely free, so feel free to invite others who you think will also gain from being a part of this community. And for any of you who do not know what Mesh Energy do, we're an independent and holistic energy consultancy. We're based in Surrey, but work on projects all across the UK and the globe. Primarily, we work with design teams and architects to make the sustainable design process as simple and as cost-effective as possible. That's everything from me. I'll now pass on to Jasper to go over his presentation. There we go.
Okay. So, hello everybody. Hopefully you can see my screen.
Yes, we can. Perfect. Thank you.
Good. So I'm going to talk to you about where we've come from as a business and how we've incorporated sustainable construction methods throughout our careers and materials we've chosen and the systems that we've developed and build with now. I've got a few videos to play during the presentation, which give me a little bit of a break, but hopefully you'll find them interesting. And as questions can come at the end as well. So if we get into, if there's not too many of us, we can have a little bit of chat at the end, that's fine. So we're going to look through how timber framing has moved forwards, where it started and where we're at now, talk about off-site manufacturing processes, modern methods of construction, and then I'm going to discuss a little bit about the materials that we use, particularly cellulose fibre, warm cell insulation. There's a plethora of different materials, of course, that we use and reasons that we do use them, but I'll concentrate mostly on the insulation and touch on some of the others. So just to give you a bit of a history about our company, we set up almost 27 years ago now, and our focus was on particularly on post and beam construction, a lot of renovation work and barn conversion type work, but we soon got involved in new build construction, and timber frame, as you can see from these photos, was certainly our focus. Along that way, along our route, fairly early on, we looked at sustainable insulation, and we discovered cellulose fibre insulation made from recycled newspaper. And so we bought into using that for our own projects, and that then developed as a business in its own right. And the great thing about that was that we've worked with some of the best architects in sustainable construction around, and we've learned a lot from them, builders who've been building to these methods. And so we've looked at all the different systems, the different materials that have been used, and came to the conclusion of what we felt fits best for our business and giving a really good product at the end of it. So our company setup is we've got the insulation division, where we've got installers all around the country fitting the warm cell, and that's from timber framers through to installers working for others, builders, etc. Construction, we used to work very locally on the construction in our immediate area within about an hour's radius, but we've now set up a workshop in Welsh do off-site manufacturing and apply materials for the sustainable construction, airtightness testing. So all appropriate and linked to what we need. Xfloc is just several deliver the machinery which delivers the installation. So we were working from our barn conversions on my yard, but we now have, in the last 3 years, been working full time in Welshpool, where we bought a site, built a workshop, steel frame, portal steel frame workshop, but clad with fully insulated panels. And the first building we built in there was our offices, which we designed and built and certified to the House of Fire standards. As you can see from this, clearly timber is our focus, and we use it everywhere we can and demonstrate it pretty well in our offices. So timber framing, timber construction methods started with I-beams, and a very common question we get is, I want to use traditional construction methods. And by that, they're talking, builders might be talking about foamed concrete blocks, cavity wall structure, which is, in my mind, not particularly traditional. So we like to think that timber frame construction is very much a traditional method of building, but using modern methods. Post and beam, that would have been the start of it. Oak, some softwood, but mostly oak would be the originality of post and beam construction in the UK. But that then moved on to regularized softwood construction components. And this particular building, I like to show it because it shows the history, but also the longevity of what timber frame building can do. So using natural materials, using these sustainable materials, a lot of people think that they won't last very long. Yet, if you build right, detail right, they can last for an extremely long time. This particular building, we took the tin off the original building. It's one of the tin chapels, which were particularly in North Wales, Shropshire areas. I'm not quite sure how far they reached around the country, but there was a lot of them built, and this one was converted to a house. And stripping it down, we found that the actual original frame, which was very old indeed, was in the main very sound. It was only failed in areas such as where the ground levels have been left to rise, or around where tin had rotted and not been repaired. So I firmly believe that building with these sort of methods, sustainable construction, timber frame materials and insulations, natural insulations, can last for an extremely long time. When timber framing became more mainstream, it was using a 90mm CLS timber, which was the only insulation requirements that were needed at the time. But when in the early 2000s, we moved on to a higher standard in building regs for insulation, the next available standardized construction component was 140 timber frame. And so that's what was used. But as you can see from these photos, there's a lot of pairing of timbers for supports, for lintels, etc. And that is a coal bridge through the structure. So to allow for this, technically you can use a default figure of 15% timber fraction in your building design. Yet, if you do an accurate measure and calculation, you'll find that there is in fact possibly up to 25%. So that's 25% of the area of wall uninsulated. So mitigating that, we would look at fitting extra components to the timber frame to reduce the coal bridging, to thicken out the insulation levels. But this was quite a fiddly way to build and to insulate. So we looked at other methods, and posi joists, a metal strap structure has been used by some people, but you do actually get quite considerable coal bridging through the metal web. So a twin frame system was adopted, and that has been the method used for many years now for building super insulated buildings and up to Passive House standards. So that's where you have two separate walls. One could be structural load bearing, the other one could be just a thickening out and reducing the Coleridge, such as the Larsen Truss method, where a smaller section of timber is fitted to the frame, strapped together with fins of OSB boarding, for instance. But again, can be a bit fiddly. So we've adopted an I-beam construction method, which is using minimal amounts of timber, but very robust and very strong. So as you can see, the web section is all that is giving you contact through from outside to inside of the structure. So you get very much reduced Coleridging, and you can build to quite a few different depths to achieve U-value requirements that you might need. So particularly useful for passive house buildings. This is a simple drawing of how that goes together. So you have your I-beam structure boarded externally with a breathable board and boarded internally with an airtight, vapor-tight board. Service battens fitted so that when you fit your electrics and plumbings, you're not running them through the airtightness layer, so you reduce that risk of air leakages and vapor risks. And it actually speeds up construction methods very quickly. So off-site manufacturing. So typically, a lot of buildings are still built on site, yet modern methods constructions and off-site manufacturing is certainly becoming much more prevalent in mainstream construction. And timber frame certainly is a really good way forwards with that. All these reasons for doing so, you essentially build much quicker, more efficiently, less time on site. So monitoring waste is much easier in off-site methods. So just looking at the categories, how off-site manufacturing modern methods of constructions are categorized. We work primarily in category 2, which is closed panel off-site panels, which are then brought to site and assembled on site. We've done an element of volumetric. That's where you're building boxes, bringing the boxes to site and assembling them on site. That can be very useful for bathroom pods, plant room pods, for instance, or quite often it's used for hotel type construction methods or student accommodation, where you've got a very repetitive build system required. And then category 3, which is the post and beam element, we still use post and beams, ridge beams, supporting beams, etc., but they become part of the whole package. This is an overview of our workshop and how it works. I've actually got a little video to play now, which will give you quite a good, it's a walkthrough on that. Let me know if you can't hear.
Welcome to PYC, the House Building Factory. We're going to have a one-shot tour through our passive house offices and the workshop. So running down the corridor, we go into the meeting room here on the right. This is where we'll have client meetings, CPD presentations to architects, team meetings, etc. You can see we've featured timber, Tianos posts and beams for supporting, birch face ply, lighting trays, poplar tables, etc. Running through back into the hallway here, tongue and groove glue lamb, past the dining room, up the stairwell where we've used tongue and groove glue lamb for the treads as well as the risers on the stairs. Copper pipe in handrail. Now up into the main office. MVHR pipework along the perimeters there. Sound cell on the ceiling to cut down the sound. There's Ben, project manager, behind the screens there, Molly and Leah. We're going to head out through to the workshop. On the walls we've used 7 kilometres of Douglas fir. There's the sign, PYC sign and logo made from Medite Extreme. And around to the end of the building where the main entrance is, we've got a 5-metre doorway which enables us to get Arctics in and out for moving large pods, offloading packs of materials should we need to. We buy the I-beams in 13-metre packs, and they then get rolled onto the cutting table. Here, using the Tiger Stop system, automatic push stop, Carl is cutting and prepping sections of I-beams for panels. They'll get stacked, ready to go onto the tables for forming into the panels. Here's one that Solly's working on, a roof panel with a skylight opening in it. He's drilling holes in the ends so that we can inject warm cell into each individual panel. And then on the next table here, getting ready for boarding, lining up the noggins. There's Tim and Brooke. And then across over on this section, Bobby and Matt are moving a panel which is finished. You can see the service zone from the underside there. That's put onto the stack. With Ryland here, he's going to be injecting the warm cell with the Lance system, so dense packed warm cell down each void. Once all the panels are completed, they get stacked, wrapped with polythene, so they're fully weather protected. They then get stored outside. Just around the corner here, we've got a couple of houses stacked and ready for delivery. All the polythene gets brought back to site after it's taken off and it's recycled. There's the stacks of warm cell, and then our storage racks and bays for the boards and beams. And Dan here is loading panels onto a lorry for a job up in London. He's stacking in an order so that when they arrive to site, they get offloaded in a sequence that suits the craneage and fitted on site. Hope you enjoy the visit. Look forward to meeting you sometime soon.
So getting there to that point of where we're delivering panels and houses onto site, there's quite a long process in design. And so it's not just design of the building, it's the engineering design of how to build the building. Early engagement is a key to getting this right, and that helps avoid waste. For instance, there's methods of optimizing your centers. So your boards, typical board sizes are 2.4 meters by 1.2 meters. So if a panel can be designed so that it has 600 centers and finishes on a 2.4 or a 4.8 length, then that optimizes the use of that timber and removes that waste in offcuts. Although offcuts can be used for other aspects, getting that early look at the building and understanding how the design works can really make a big difference. So for instance, if you put windows in which are 500 mil wide, for instance, then we're not trying to be restrictive on design, but little tweaks and changes can help reduce cut-off sections and wastage. So we really strongly focus on the fabric first element, and if dealing, as we're saying, early engagement, if we're dealing at concept stage and working through the building, we can really optimize the performance, the construction, making sure that there's no unnecessary complex engineering issues to deal with, and you can produce that high performance building. Then lastly, on the design element, you can look at the renewables and the mechanics of running the building, such as a heating system, and by having a really highly performing fabric, you can actually reduce the elements and the requirements that are needed for that. Passive House is the best standard that we see, so we'll try and make sure that most of our buildings are modeled through the PHPP, the Passive House Planning Package software. So looking at the key points for getting to that passive standard, that super insulated standard, you've got the coal bridging, so using an I-beam or a twin frame system, dense pack cellulose fiber, the recycled newspaper, warm cell insulation, air tightness, key to use good components, good materials, such as boards and membranes and tapes. Wind tightness is also important. That's ensuring that on a windy day, you're not going to get wind blowing into the building, which will effectively be like sucking heat out of a building. It'll cause a rapid cooling unless it's wind tight. And then triple glazed windows become very much a standard for both for performance, but also comfort, and fantastic for acoustics as well. And as you've got a airtight, very airtight building, you need to make sure your ventilation is right. Of course, you can open a window, but if you have a mechanical ventilation heat recovery system for the times that when you don't want to open a window, you're not getting heat loss by sucking out stale air, but not replenishing it with fresh air. So with the MVHR, you do get that very fresh air feeling and living in such buildings. It's another little video for you. This is about Passive House, and it's all about the fabric of a building. So it's a very quick snapshot of why it works. And I'm sure some of you are very familiar about Passive House, but I'll play it so it's something useful for demonstrating to people who haven't got much of an idea.
Passive House explained in 90 seconds. Does your house have a heater in the basement or maybe a fireplace? Probably also a central air conditioner or maybe a window unit. Did you ever wonder if it was necessary? In 1991, a physicist in Austria, Dr. Feist, built the first passive house. Here's what he did. 1. Proper insulation. It's just like wearing the right winter jacket, it also doesn't need a heater. 2. No air leakages. There should be no holes, small or large, to let hot air out of the house. 3. No thermal bridges. A thermal bridge is like a road for heating energy in which warmth can travel right through your walls. As a matter of fact, most of our houses have thermal highways in our walls where heat can easily travel to the outside. Plus, the house needs proper windows most of the time with triple pane glass. It needs to be oriented properly so the sun can heat it in the winter and shade is provided in the summer. And it uses an HRV, a device that provides the inside with fresh air without letting the heat out. Add all these things up, and it turns out your house doesn't need a heater or air conditioner. So where does the heat come from? A passive house needs 90% less energy, and that can easily be supplied by your body heat, the sun, your appliances, light bulbs, and even your TV. This saves you a lot of money on your heating bill and helps preserve the environment. Did we make it in 90 seconds?
You bet we did.
So a quick overview on this slide showing you the methods of construction. So we have the airtight board, that's the green board, tape joints, tape to the windows. So you've got that seal, which gives you the airtightness, but also the vapor control. And then this, within the surface zone, your electrics, etc. We have worked it through so that the panels run past the floor cassettes. So typically on timber frame construction, you bring your floor cassettes at floor level and then your floor panels run over. That can lead to cold bridge complex details. So using a ledger in this system works very well. And then dense pack insulation, the warm cell insulation into the partition walls and floors can then really give you good acoustic benefits. So working through this, quite a new slide which I picked up on, robbed it from a presentation I saw recently. Mark said I'll give a great presentation on Passive House. And just anyway, looking at this, you've got, typically we look at plans when they arrive at post-planning stage. So when the design is fixed, and sometimes even designs get fixed and tender comes in, prices are too expensive, then people look at value, VE, value engineering. To do that post-cost realization is a big mistake. If you can check on all of these aspects early doors, you can then really make sure that the building is going to perform. This not, as I was saying before, doesn't just apply for use of materials and making sure you're not going to be wasting your materials. It's also about design and structural engineering aspects. And so to optimize that to the budget is really, really important. Looking at that, we would go through U-value calculations, getting the best performance as required. So depending on the form factor of the building, could give you a dependence on what insulation levels you might need. We're looking at the coal bridging, so checking on side values. If there's a complex roof, such as a flat roof, then we would do WUFI calculations, which really gives you good analysis of the structure, ensuring that you don't get interstitial condensation, which obviously is the last thing you want in a building. And then the key element would be the PHBP, the passive house design element, which not only looks at thermal performance, coal bridging, etc., but it looks at overheating issues and many, many aspects of the build, which really give you the benefits of ensuring that the performance that you're designed is realized in the construction. So once plans are received, GA drawings will be done, frozen drawings, and then 3D modeling can be drawn up and look at engineering aspects, liaise with groundworking engineers to ensure that the point loads are identified, and if there's an opportunity to optimize that construction, that engineering, that's the time to do it. And that brings us on towards the manufacturing drawings. But along the way, there may well be probably MVHR unit fitted and ducting throughout the building. This can be brought in as a separate 3D model, the design work can, and so we can integrate that within our timber frame model to ensure that there's no clashes. The last thing you want to be doing on site is finding out that your pipe has to go through a steel beam or a large timber beam which can't be cut through. So that's just optimizing and making sure that all meshes together. Fire risk is certainly an element that has to be watched out for, and particularly when buildings are adjacent to others. And so a fire risk assessment will have to be carried out to ensure that that's not a problem. We've carried out some fire tests on our structures very recently, and so on an I-beam frame and a twin frame, and we've had some excellent results on those, which I'd be happy to share with you should anyone need them. Of course, we've got different detailing, so dealing with coal bridging around your slab, so making sure that you've got coal bridge free structure there, and likewise the floor cassettes using the suspended the ledger-based system, and other details that we can provide. And so, for instance, Velux windows, we used to just do a square cut hole, but now we can do all the forming of the chamfered reveals, which speeds up again site work. And then your timber frame drawings, where you get your cutting lists, cut everything to size, packs, then ready to lay out and manufacture on your work tables. Board one side, flip over, board the other side, and then they get injected with the winter insulation using the Lance system right there. These are finished panels, and so we've got here just again showing you the airtight board. You see there's a bottom cord running across there, just tying that through so that you don't get a split at that point during construction, of course. And left out the service zone battens are left out here because that's where the ledger will sit. And then here we've got a heavily branded membrane, yet if, for instance, there's a shadow gap detailing required for the boarding, then we can we use a completely black membrane with no labeling on it, which doesn't then show up in the finished product. On site, our first job would be fitting a sole plate around the concrete, and this is actually a basement, so it appears much higher than perhaps a standard construction, but the sole plate gets fitted, and then the floor cassettes, the wall panels come on, and producing all the way up with scaffolding's already up. So these are sort of images you'll see of a finished building. And then even complex sites and tricky places to build, you'll have, we've got a rotary 360 crane where you can fit in quite neatly. This is in London, and offload panels and then bring them over onto site. And part of what we would be offering is bringing in crates of windows or plasterboard crates to drop onto floor levels as one's moving up. Just saves time on site and saves that extra work. It's easy to do it when you can. So our reasonings for building off-site, follow in line with pretty much most other people's, I would have thought. So we'll enable to get everything planned and built prior to coming to site, of course, and that ensures that we can get the best performance in our panels. And I think probably one of the biggest reasons really for us is the material usages. We can optimize timber, the timber I-beams, optimize the cutting so that we maximize what we've got with the machinery we use. And I'll explain about the warm cell later, but we don't get any waste at all with that. That's completely reused, anything left over. And we're working locally. We've got local labour, so there's not a lot of commuting to site as well, apart from the build time, but the build time is a relatively short process. And when looking at the circular economy, we are aiming to improve what we do all the time, so designing out the waste, trying to use products which can be reused. And so everything that we would use in our construction methods are natural materials, so timber-based, or cellulose carbon timber-based materials, which can be used at end of life, although I would very much like to think that end of life is a rare position to get to, because they do last for a very long time. And part of that build process, the design and build process that we work to, we've been recently working with, well, over the last 2 years actually, with BOPAS, Build Off-Site Property Assurance Scheme. And so basically that analyzes every aspect of the business, but then also the building method and the materials. So working through from recruitment of staff through to handing over a project to a client, everything is analysed and checked, and quality control and engineering wise, every single aspect. This gives us a 2 lifetime mortgage warranty on the build system, which equates to 60 years. So very useful. Part of that was the fire tests as well, which we've brought towards. And constantly changing. So we're always looking at it and looking at how we can improve it. So optimizing transport loads, so making sure that we can get best loadings we can on our lorries, and how to improve our services. So it's a very important part of any business really, is to constantly review and monitor how things are working and how to get things better on material usage as well as labour works, etc. And so in that process, we look at design for manufacturing, so improving on the manufacturing process, reducing materials. So if, for instance, we think that something might be over-engineered, we can actually increase from 400 centres to 600 centres, for instance, and we will be looking and analysing that. And then assembly methods, we look at design for assembly and, as I was saying before, transport logistics, checking on what processes and materials we're using and how we can improve on that. And very much more recently, over the last 2 years, it's been, I'd say over the last couple of years, we've seen a much stronger focus of people looking at designing for net zero. And whereas, we've had projects which have swung out to us from where they've been designed with carbon intense materials in process, so high embodied energy materials, and looking at ways to improve on that. And so timber frame, natural building materials, insulation materials has really helped improve that. And then the construction side, again, looking at how to optimize and improve everything on that respect. So that's my talk on the timber frame. So I'm now going to look at the insulation aspects. So we'll look at design, where design comes in on insulation, and then practical fittings and improvements on how that works. And specifically, as I said before, we'll be looking at cellulose fibre dense pack insulation. So if you've designed, and one thing we're very keen to impress upon people is that if you're designing to building regulations and you don't get something quite right, then you've actually got a substandard building, because building regulations is the minimum legal standard that you can build to. So we're always trying to push the boundaries on that. But typically with insulation, so if you've got gaps on the inside of your wall structure, inside and outside, you're going to get airflow through. That's going to cause cooling of the building, so reducing the insulation value that you thought you were going to get is going to be reduced. Likewise, gaps top and bottom, you're going to get convection looping, which is going to again cause cooling. So dense pack, fully filled panels is the way forwards to ensuring that the U-value requirements are met. These typical photographs of sites where it hasn't been done quite right, and when you do air tightness testing and so depressurizing a building and thermal imaging, you can really identify where all those Coleridge points are, be it through Coleridge structure timbers or gaps and cracks in insulation. Another little video for you. This is about the warm cell insulation, so this explains more about what it is. So manufactured from recycled newspapers, it's quite an intense process and quite high levels of engineering goes on. So it is essentially recycled newspapers, which are cut, milled to optimum size to produce the best performing insulation. But you've also got the addition of boron salts, magnesium sulfate salts, which are mined, ground up and added to the paper. And they're put in place to prevent mold growth, keep insects and vermin out, and also give it fire protection. And how that happens, they can be, and some manufacturers would just add them and mix them, dry mix them. Yet we heat the insulation and the salts up to 80 degrees, and so that makes the salts tacky so that they bond extremely well, so you get very good adhesion to the paper and get that uniform full protection right through. So that process happens, and then bale can manufactured and delivered to sites. Just to recap on the aspects of the insulation, so you've got thermal conductivity, that's the lambda value, which is how you can work out your U value. So it's 0.038, and that's allowing for potential, we get a penalty for a potential of humidity within the insulation, although reality is in the design that doesn't happen, but so the performance is based on that figure. I guess the key performance benefits of cellulose fiber, because it is very densely packed in, it typically gets installed depending on thickness of walls, pitch of roofs, etc. But it's anywhere between 45 and 65 kilos a cubic meter. So that dense pack really helps for overheating issues. So for instance, if you've got like a warm roof structure, sunlight beating down from the outside, it'll heat up the insulation layer on a lightweight insulation and start heating up the room below within about 3 or 4 hours. Yeah, U value for U value, if you use a dense pack insulation such as cellulose fiber, that heating process takes up to 11 hours. So the absorption and that decrement delay you get from the insulation really helps to prevent overheating. But also in winter months, throughout the year really, you get that stability of temperatures. So you don't get this sort of peaks and troughs of heating. You flatten that curve and get a much more comfortable building to live in. That's the specific heat capacity factor. That's a combination of lambda value and weight density. And the manufacturing process is obviously it's paper made from timber, so you're locking carbon into your building. So with the addition of timber frame, timber boards, and natural fiber based insulation, carbon based, you're locking carbon into the building, which is obviously a great thing to be doing. And so the embodied energy of in the manufacturing process is extremely low. So whereas some products will take quite intense heat and energy to be produced, relatively cellulose fiber insulation has a very low embodied energy. And so this has been calculated by BREEAM to give you a global warming potential of minus 1.5. That's allowing for all the material supplies, transport, etc. Part of technical backup services would be providing U-value calculations based on all the different materials. So we'd look at all the different materials and work out what the U-value calculation would be. But that would also cover condensation risk, and we could advise accordingly to remove or add certain materials to ensure that that wasn't going to be an issue. So we mentioned fire before, and so we have had some laboratory tests carried out, but this is a very basic crude test which very clearly demonstrates. So this is using an oxyacetylene blowtorch, melting a penny on my hand, and temperatures getting up to 1,000 degrees quite easily and sustained at that. So as you can see, the penny melts and the flame causes charring of the insulation. But yet you take the flame away, then that charring dies down and the flame goes out. So basically what happens is with the boron salts, Epsom salts, in the paper, by water crystallization, when the heat's applied, it drives moisture into the surface, which helps the charring process, and that actually slows down. So we can't be saying that it doesn't burn, but it burns extremely slowly. So the key point really is that fire in buildings, it's not about what burns or doesn't burn, it's about how the whole thing performs in that situation. And slowness of burning is obviously key to enable escape and putting out fires. Where the insulation can go, lofts, very straightforward, very simple, put it to whatever depth's required. Sloping ceilings for warm roof structures, all external walls, partition walls and floors, and party walls for acoustic reasons. We never put it in a brick and block cavity because there's too much risk of unmanaged condensation risks on that and potential leakage through cracks in brickwork. So it's definitely a no for cavity walls. Just to recap on some of the points. So one of these is the fact that we've done quite a lot of airtightness testing pre-installation and post-installation of structures, and found that we get 30% airtightness improvement, which is sort of logical really. You fill up an empty void packet full of insulation, it's going to improve it. But we did some tests to prove that, and we've also done quite a lot of acoustic testing to demonstrate the sound reductions. So for instance, we did sites where we had to test 20 houses over 5 sites and on party walls, and building regs requirements were 45 dB sound reduction, and we were achieving an average of 54, which is exceptional. So the installation is fitted using the X-Flock machines and stemming from job-in site machines, the mini-fan machines, through to factory fill machines. And the methods: open blown into lofts on site, injection perhaps on site, through wall into walls and sloping ceilings. Typically, a lot of that happens with curved needles, so you get these needles which inject through to, you can reach to all corners of a void to inject to the densities required. This is the off-site manufacturing process, so this is extremely economical and efficient to run. So you've got the big grey box in the back. It takes a full pallet of insulation, and that then sits in the box here with a ram pushing it up. It rakes off the top of the machine pallet and drops it into the hopper of the machine, where it's refiberized, then blown under pressure down through to the production line to an injection plate, where it's injected into the panels on a working table. And that's all automatically set, and this injection plate switches from nozzle to nozzle to the panel voids. Just to recap on the installation methods: so you've got lofts, open blown, sloping ceilings, injection into walls. Used to spray it with a bit of water for open stud work, but that's very uncommon these days. And then this is the system we use, which is injection with a lance through to stacked panels, or then you've got the full production line factory systems using the big hopper. Of course, we've got to ensure that everything's been done right in the construction methods. So we'll be looking at density checks to ensure that the correct density has been installed. We've got software, which is a pH ribbon Tim Martel did for working out the carbon content of your structure, so you can work out, we can identify exactly how much has been used in timber-wise in the panels from our software, and of course the insulation, and so that can be put into the equation. And then other aspects is the PHPP calculations, of course, the evidencing of that, and then airtightness testing results, cold bridging, new values, etc. Just going to run through a few projects where we've worked using these materials. And so this is classed as one of the most sustainable buildings, commercial buildings in Britain. It's a large university building in Norwich, designed by Architect Type. And having visited it a few times, when it's completed, it's got fantastic feeling to the building. The air quality is really good, and there's a lot of natural materials been used as finishes internally as well, and giving you a really comfortable building to work in. Schools, there's been a fantastic amount of schools being built using these systems, and the results, the post-occupancy monitoring of these has shown that not just running costs, but again, the comfort of living and working in these buildings is fantastic. You know, air quality is improved, carbon dioxide levels are reduced dramatically, so that attention spans for kids, etc., is much better. And you can, with the MVHR systems, also put in filtration systems if you needed to for pollen allergies, etc. And these are just examples showing sort of broadness of latitude of work that we've carried out and different buildings. And having worked on Passive House since its introduction to the UK, which was back in 2008, having had the opportunity to work on some of the first buildings has really helped us to learn a lot from the designers and architects at those times. First Passive House building in Wales near Machynlleth, both of the first two buildings by JPW Construction. And then timber frame can have quite a lot of variety in styles of buildings, so and strength, carrying weights such as a sedum roof, different sorts of shapes, finish styles, timber, and very conventional buildings. This is one where we did a lot of the testings down South Wales. A lot of the housing associations were building with timber frame and warm cell, and so this was one where we did one of the sites where we did robust detailed testing for the party wall. And then timber frame doesn't have to look like timber frame. So for areas where you've got to fit in with the local vernacular, or you can't break the boundaries, then you can use masonry on the external. So this is a 4-story timber frame building. So you certainly wouldn't notice it from looking at it now. So from that point there right through to over here, it's a 4-story timber frame. Even the chimneys are actually timber frame, obviously not used for fires. They're ventilation stacks. And very contemporary buildings. This is one which we built and fitted the larch cladding and steel roofing. So this was a passive house, and interesting about this, because there was root protection demands from the trees which had TPOs on. Couldn't do any digging on the site, so it has a suspended floor with a concrete-free foundation system. So that enabled us to build the building with very little impact on the environment. And then some fantastic, great schemes. Mikhail Riches designed this project from London and built it in Norwich, and they've got more going on in York. And it's great that council's been taken up on board looking at passive house and sustainable construction methods. Great performance coming out from these buildings. And this is yet another one where we were working as consultants on. So this was using heat-treated poplar cladding. This was designed by Archetype, and we worked for for Lowfield and SJ Roberts Construction as consultants. So that's an overview of what we've just been discussing. And please, let's have a look at any of your questions and see if there's anything you want to ask.
Thank you for that, Jasper. We've got quite a few questions that have come in. I think you already mentioned this, but Laura mentioned what design stage do you get involved in? At what design stage do you get involved at?
Ideally at concept.
Concept, yeah.
Ideally, but typically that, we don't often have the opportunity to do that. And the reason being, it's good to get engaged early. As I mentioned before, we want to be designing to a budget, but also optimizing the building for energy efficiency and structural performance. So for instance, if early design, we might be able to say we can move a wall by 500 mil to pick up a point load from a beam above, or align partition walls from the ground floor to the first floor. All little things like that can really help. Trying to avoid any sort of costly engineering by simple adjustments at that early stage.
Yeah, okay, that makes a lot of sense. We've got another one saying, can your system be used for rear and loft extensions in existing buildings combined with external wall installations on the existing? So can yours be used as like an add-on to a building?
It certainly can be, but it is quite hard as an offsite manufacturer to deal with small projects like that, because there's quite a big overhead in setting up to produce panels, etc. So quite often those end up being, and unless they're of a large size, quite often they end up being stick built, but there's no reason that you can't do an on-site method of exactly the same system. It's just, obviously it's balancing out access, logistics, and costs.
So with the insulation as well, would that affect how the heating of the house would happen if you had an extension with your passive house concepts behind it in comparison to the house that wouldn't be built that way?
Well, you can use the same materials, you can use the same insulation values for your extension, and if you've got a house which isn't performing very well, certainly don't turn around and think, well, okay, well, there's no point in doing anything efficient with our extension because we haven't got anything very good to start with. If you do a very efficient extension, it can really help the overall benefit of the building. So if you're increasing the footprint, any improvement you do with your extension side, and if it's over and above what you've got existing, then your average heat load is going to be much better. So maximize what you can do in your extension or loft conversion, because it will only but benefit everything on the build.
Okay, interesting. We got another one from Laura saying, what procurement route do you normally use?
Ideally direct engagement, there are times when we've worked and been nominated as timber frame manufacturer, or we have worked at tender stages and it's been open tendering process. If we can start early, we can cost at that early stage and help secure what those costs are going to be. So we would work ideally for the client, perhaps with a main contractor, subcontracting as a main contractor. So yeah, it depends on what restrictions there are in procurement. I think the whole procurement route in construction has got to change. There's a lot of things which are quite broken in the way it does work at the moment. To get the best performance of the building, the best construction methods, I think it's essential to try and engage early on. I keep saying that, but it's true.
Yeah. Okay, so I think we've just got 2 more questions, and one is, can the insulation be recycled again after use in the house?
Yes. So we have had situations where we've had to go back to a building we've built and cut into it to put an extension on, and so we've removed wall sections, removed the insulation, and as long as you take it out cleanly, it can then be reused as was. So
Okay.
just we've also, our machinery will actually extract as well as inject, so we can suck it out and reuse it. Yeah.
Wow, that's definitely really useful. I think that is everything. I think that covers the last question as well. Unless, Laura, you want to explain that a bit more and take yourself off mute. But I think other than that, we've covered all the questions. It's been a really useful webinar. Obviously, covering recycling for insulation is incredibly useful for all the architects. And then also the concepts of passive house are very interesting, and I think a lot of firms and consultancies are looking to the concepts of passive house for new buildings. So yeah, that was amazing. Thank you so much for coming, and we'll have to do another one in the future, I think.
Thank you. Just another note really is, if anyone needs to get in touch, please do jasper@pycgroup.co.uk. So you'll be able to find us on the web.
Perfect. All right, I will end this now, but thanks for everyone for coming.
Thank you all.